My name is Michael, and today I'm going to discuss a couple of reasons why databases cry at night. A word or two about me. I've been programming for quite a while, and you can see some of the things I worked either on my previous job or just in my spare time in my GitHub repository. Currently, I'm working at SAP as a senior developer, but for the last 6 years or so, I've been working on a NoSQL document database called RavenDB. But the talk will not be about RavenDB. While I was working on RavenDB, I did various things. I developed and maintained features in various levels of abstraction, starting from low-level stuff such as storage engines, such as indexing engine, tweaks here, tweaks there. I did work on distributed stuff like replication. I did work on clustering protocols, and also I dealt with support and post-mortem investigations after disasters, after various issues in production. I did investigations, and some of the conclusions and thoughts I am going to talk about are based on my experience and what I've seen in various projects, what happens in various projects. And what I sometimes saw, I'm not sure how often, but enough to notice the trend that some developers think about databases as kind of magic boxes that you just issue queries and it does some magic and returns results. And databases are not really magic. They are abstractions, and quite leaky abstractions, to be honest. I agree wholeheartedly with Joel Spolsky. And quite often than not, those abstraction leaks become issues, or performance issues, or usability issues. And I'm going to show you, at least try to prove to you, that knowing just a little bit about what happens under the hood of a database can help with either mitigate or prevent performance issues from happening. So in general, databases are quite a big topic. So I chose to concentrate on a couple of topics that are common to many databases, because databases, in the end of the day, have very limited set of algorithms they're implemented with, and things you see like API and also all the bells and whistles are just built on top of those common algorithms. Now, let's start with storage. It just works, no? Kinda. Here is a little story or riddle. Why the hell did it happen? Some time ago, I got a call from a customer that they had a RavenDB backups fail very soon, seconds after they started them. And after a cursory glance on the system, I saw that they didn't have any issues with system resources. Memory utilization was low, CPU usage was also low, and according to histograms in their monitoring, they were never the issue. And it was dedicated machine, so nothing could have interrupted that. So that was weird. That the backup tasks were failing seconds after they were started. The thing is, it was weird. It looked weird because that part of code was never an issue before, the dealing with backups. So I looked at the what was happening, looked at the customer scripts and saw that starting at the same time. That looked a bit problematic. And after I looked what kind of databases did they have, and they had lots of tenants. This means many databases that were running on the same server, and all of the databases, all of the tasks for all of the databases were starting at the same time. And what is more interesting, that they used SAN storage, which means network drives, to store the backups as a backup target. And storage, network storage, has very one interesting feature, or quote unquote feature. They can receive timeouts if their latency is, if they're too overloaded. And indeed, after I looked at this queue length, I saw that was an evidence that they had a bottleneck at the storage. And hard drives or storage has throughput, just like anything in computers. And if you try to write at the same time, issue too many requests at the same time to write something, this means that something will go through, and the rest that they go over the capacity of your storage will just form a line, form a queue, and wait to be written. And this kind of you can take a look at this queue length in various third-party storages, monitoring solutions, dashboards such as Zabbix, for example. And also in Windows, if you have Windows servers, you can even use performance monitor, built-in performance monitor, good enough to look at this queue length. Very useful to look to check if you have bottlenecks in your storage. And the thing is, too many requests were just making the writes very slow, because the disk was waiting for the writes to actually get written. And what happened is that some of the tasks, some of the backup tasks started getting timeouts, and most of the tasks failed. Because if you have more than 200 tasks fighting for storage, will cause issues one way or another. If that was hardware attached to the server, it would have just caused the writes to become extremely slow and will take you a lot of time. But network storage just caused timeouts, and things went down the hill from there. For the client, the solution was pretty simple. Just make the backups happen one after another. And this way storage wasn't overloaded. So that was it. But here is another thing to notice about low available memory, and the load on storage. If you have low memory, operating systems will start dumping memory into page files, which is virtual memory. And in this way, you will create additional load on storage, additional write requests, and so on. And usually the dumps will be fast, and in this way you will cause your system to crash, and this will cause additional performance issues. So in general, I would suggest to first and foremost load test your code that handles databases, see what kind of throughput you have, and ensure that you have, if you have your own on-premise storage, ensure you have enough IOPS for that and throughput for that, just like the scenario of multiple backups starting at the same time. They didn't load test that kind of scenario. And if you have cloud storage, Amazon Azure have their cloud storage, and databases usually have an option to backup to cloud storage. ensure that your cloud storage has enough performance, and IOPS, by the way, means input output operations per second. And when we are talking about cloud storage, there is something called IOPS provisioning. This means simply ensuring your storage will have a minimum amount of IOPS. And obviously, if you provision more IOPS, you pay for that. But if you need the performance, that you need it. Also, load testing is pretty nice to know the limits of your system. To first make sure that if you have low memory, you still have the capacity to handle your load. And second, to know when to scale up your system, add databases for load balancing, and so on and so forth. About a little bit about how I check the storage if they have enough throughput. Usually I like using three tools: Process Monitor, Crystal Disk Benchmark, and ATTO Disk Benchmark. And you can use other tools as long as they have the same functionality I'm going to describe, because the tool doesn't matter. What it checks, obviously, that's what matters. Regarding Crystal Disk Benchmark, it's a nice tool to check the IOPS, essentially the IOPS of a hard drive or a storage. It can do random or sequential access. Random access means the storage accesses, when reading, accesses different sectors that are far away from another, and sequential, as you can understand, it just accesses the sector sequentially. Databases usually need random reads because they need to, and as we will see later on, the storage data structures they use require random access. And this means that optimal performance, the better your random access reads, the more optimal your storage for database storage is. Now, regarding to queues and threads, essentially, Crystal Disk Benchmark can simulate either multiple threads trying to concurrently write stuff on your storage, or can simulate multiple write requests at the same time. Essentially, what is the most important thing is to create small reads or small writes, test for small reads and small writes, and test for single-threaded writes, because again, this is something I'm going to describe also a bit later on. Databases usually use single-threaded writes and small batches of data each time. So the faster those particular performance will be, the better your performance of database will be. The rest of the tools I will discuss later on because they are tightly tied to the topics I'm going to cover later. But for now, let's take a look at a little experiment that I did. I used a key value store, transactional key value store, the LMDB. It's not the name itself, you might not have heard it. This is an open source, old and battle-proven key value store. It's used in various open source projects, which most of them I don't remember their names. One of them would be OpenLDAP, if I'm not mistaken. And in any case, it's one of the oldest and one of the better written databases in that class, key value stores. And I did two performance experiments. Two times I wrote within 100 transactions, 100 key value pairs, And one time I exactly the same values each time. One time I wrote those values with sequential keys, and one time I wrote those values with random keys. And take a look at the results. Now, the y-axis is the number of storage seeks which happened in each transaction. What do I mean by storage seeks? How much times the storage tried to read another sector, switched from reading one sector on the storage, physical sector, to another, right? And as you can see, you can see here two interesting things. First, the number of seeks steadily grows with each transaction. And second, what is more interesting, the number of seeks for sequential keys is consistently lower per sequential keys than per random keys. And if we aggregate total time that took each transaction to commit, we'll see that it's the same pattern. Sequential key transaction commits with sequential keys are consistently lower latency than random keys. And please disregard this extra data point. Probably I had another process do a write on a storage and it threw off the measurement. But you can see the pattern if you disregard this one point in the blue line. And I did those measurements with the help of the second tool I mentioned, Process Monitor, this internal process monitor. It's very handy tool when you want to measure and see the low-level activity on the operating system API level in Windows. It can read various system level things like network. It can read registry, even calls to write and read from registry. And I use it to show reads to a file or storage based API, so file storage. By the way, if you use Linux.NET Core Linux, in Linux there is strace, a very nice tool that can do approximately the same thing. So you can do this kind of measurements in Linux as well. Don't believe me, just do this test in Linux and see what happens. Why does this happen? Here we'll see that LMDB uses a special kind of tree to store its data called B plus tree or B tree or B plus tree. This is variants of the same. The idea of this tree, of this data structure, it is self-balanced data structure. It's optimized for reads because on its leaves, it has a linked list of values. And in this way, it tries to, and successfully and succeeds to make less seeks when you are traversing the tree. And if you take a look at what kind of tree sequential versus non-sequential keys create, you will see that due to the way B trees balance themselves, a non-sequential tree with non-sequential keys will be much deeper. Much deeper, depending on how many items you have in the tree stored, but in any case, it will be deeper. And the reason why you have seen those differences in the latencies is that disk seeks, even on solid-state drives, are not free. They have overhead. Yes, on the leaf you have sequential reads, but if the tree is deep enough, you will have more random reads than the sequential reads, and that is costly. And obviously, on spinning magnetic drive HDD is much more costly. So that's one of the reasons why you should never use, if you can, obviously, HDDs for database storage. So if you have a database that uses B-trees under the hood, I would suggest using sequential keys whenever you can, whenever your business requirements allow it. Because once you get enough data, and by enough I mean order of magnitude of, say, millions of records or more, and large enough systems, you can easily get more than that. This means you will start seeing differences in performance, and the more data you have, the more differences in performance you will see. And also, an interesting side effect, and we'll talk about it and in a bit more detail later. B-trees are often used for indexes as well, and this means that you, as a side effect for sequential keys, you will get for sequential indexed things, you will get better performance for queries. Let's see one more data structure, which is really common for in databases as well. This is actually first time I heard about this from a participant in a RavenDB workshop I did some time ago. And he told me that in their company, they're using Cassandra. And Cassandra, over time, becomes slower and slower with reads. And then suddenly it becomes faster, and it's non-deterministic. So sometimes it's slow, sometimes it's fast, and the changes are not deterministic. And this got me curious, and I looked, and I found very fast, even in the Cassandra's documentation, an article about this interesting effect. And the reason it happens is that Cassandra uses second type of data storage for storage engines, and it's pretty prevalent in databases as well, together with B-trees, log-structured merge trees, LSM trees, sometimes it's called. And you can see it in databases like LevelDB, HBase, SQLite 4, version 4, if I'm not mistaken. And I think mail.ru Tarantool database also uses LSM trees. And the smallest data unit, data storage unit you can have is as a table or sorted string table. And essentially, sorted string table is a table that contains key value pairs. And the idea behind LSM tree is that the storage is divided into two parts. One is a volatile part. Usually it's B-tree or some variant of it. Rarer, but still it can be a skip list. And when you make changes in the volatile part of the LSM tree. So let's say I insert some record, then I update a record, and as you can see, the changes in the min-tail gather in the volatile. And then I will do some deletions, and then I reach the commit. Commit adds the resulting SS table to the end of the storage, and this way it's get written very fast. And that's why Cassandra is usually better for many writes than reads. And in order to read, you need to read the whole store, the persistent store, in order to reconstruct the state of your key value pair, in order to maybe it was deleted and written again. You cannot really know by reading the only at the end. Now, that is the reason why over time Cassandra becomes slower and slower. Now, why it's merge tree? Because sooner or later, and usually it's decided by the storage itself when to do it, the LSM tree executes a compaction operation. And that's not a cheap operation because it needs to go through all of the accumulated changes, or let's call them deltas, because it's more accurate description. And then after compaction, you'll see that reads become fast again because there is much less things to go through to reconstruct the state of single pair. And this means that your reads fast again. Now, the compaction strategies are different, I assume, for any LSM tree implementation. But there, for example, in Cassandra, there can be multiple types of them. Some are optimized for reads, some optimized for immutable data or time series. And by the way, you see here that you can change the compaction strategy by using standard Cassandra commands. But exactly what those strategies do is besides the point. The thing is, in Cassandra, compaction strategies are essentially optimization for patterns you have, because maybe you write much more into database than you read, for example, for structured logging. Or maybe you're using Cassandra as a part of CQRS, so you're, let's say, you're doing lots of reads and very small amount of writes into it. So you can. My point is that most databases have vendor-specific options for optimization, and if you know just a little bit about what happens under the hood, you can utilize those options to have better performance. For example, MongoDB has an option of running aggregation queries where you write JavaScript or something like that. But also it has aggregation pipelines as a special API for aggregation. Microsoft SQL has all sorts of bells and whistles to optimize its indexes. And in general, you can change even the key composition, so on. So there's a reason DBAs get their salaries, that they know those optimizations well. And those optimizations can be really game changer in terms of performance. RavenDB, for example, uses DSL to define, it uses C# link as DSL to define indexes. So, and those DSLs have an overhead, so you can use optimizations there and perhaps not create very heavy on indexes and performance. So let's take a look at another thingy. Okay, let's take a look at ACID guarantees. ACID guarantees is something that you probably heard a lot, and it's actually a very simple idea that if your database transactions support ACID, this means that your operations either succeed or don't succeed, no matter how much operations were crammed into one transaction. Your data is consistent before and after the operation, so you won't see things like dirty reads, and changes of one transaction are visible to other transactions. And one of the more important things is durability. So if your transactions report success, this means that either you have hardware failure or your server is on fire. That's the only ways you can lose your data, no more than that. Here it is worth noting that not all databases support ACID. Relational databases, of course, support it, It's a bread and butter of pretty much all relational databases, but not all NoSQL databases support it. Some support, some do not. And usually it's written in documentation, but I digress. Now, let's discuss write-ahead logs, or transaction logs, as they are sometimes called. This is a way to implement atomicity and durability. So the idea is that in addition to data storage, which is usually a B+3, you have a kind of persistent queue. And by persistent, I mean once you write data into it, it's not going to get deleted unless you have hardware failure or the storage deletes its data, something like that. So on its own accord, you can have it accidentally deleted. And the idea is that, let's say you have a transaction when you write A and B into a database. So you write it into a transaction log, then write commit. You don't write into data storage yet. You write another value X, and then you do another commit. So you have now two transactions in the transaction log. Okay. Now the trigger is often different, a little bit or much different, but usually it's either database idleness, or timed flush from the transaction log into data storage. But usually it's combination of both. But once in a while, a data from transaction log get written into data storage. The idea behind this is twofold. First of all, create quote-unquote lazy writes into data storage in order not to pay immediately the cost of actually writing the data into the storage. The second is to provide immediate feedback to the user: did the transaction succeed or not? And the transaction write succeeds when it's actually written into persistent transaction log, right? And then you return to user, okay, now the transaction is committed, everything is fine, right? And then let's say your data didn't write into, it wasn't written in the storage yet, and your database, let's say, restarts. Then the database will simply read the transaction log sequentially and reconstruct the state of your records according to transaction log. And in this way, you will have durability. Now, the trick in implementing such, one of the tricks, it's a bit tricky to implement write-ahead logs properly, but a pretty important requirement for such implementation is to have write-through writes. And the idea is that pretty much all storages, be it HDDs or solid-state drives, they all have caches which are volatile. So if, let's say, you have a power failure, this cache gets deleted. And your writes, usually, when you just issue a regular write to the file, are written to the hardware cache of your storage, and periodically is flushed to your storage, to the actual storage. Now, the problem here, when you're doing the regular writes, is that if, let's say, you have power failure, let's say you're doing regular writes, you write your transaction log, it's still in the buffer, and then your server dies. You now lost your data despite reporting okay on transaction, right? This should not happen, obviously. So writes to transaction log, it needs to be special writes doing write through. This means bypassing the cache. And those writes, it's time now to talk about one more, the last performance tool. Add to this benchmark, those writes, since they are special, as you can imagine, they will be slower. And why I like using disk benchmark, it allows you to bypass the buffer cache and create tests, to test the throughput of a storage without the buffer. And the difference will be pretty significant, I would say, because what you see here is an experiment I did with writing with ATTO disk benchmark on NVMe drive. It's pretty fast drive. So with buffers, you will have order of magnitude of gigabytes per second, and without the buffers, with write through writes, you will have only megabytes per second order of magnitude. And what's even worse, because databases usually write very small chunks of data per transaction into the transaction log, and this means that the performance even on NVMe without buffers would be on the order of magnitude of hundreds of kilobytes, pretty much. So another thing to test your storage would be to test for write through, because if you have if your database supports ACID transactions and you have very slow write through performance, this means you will have a bottleneck on transactions. And that's one of the reasons why so many databases that support ACID transactions allow you to store logs on special separate drives. It allows you to specify, because the transaction logs are often a bottleneck for database if they are stored on a very slow drive. So in theory, you could create or issue a special drive just for the logs for the transactions to be much faster, and then the data store can be a bit slower drive to make the system cheaper, for example. So this kind of consideration is a valid one, I would say. Now, let's talk a little bit about queries and complexity. What we see here is three queries, the same queries. Let's imagine we have online store, and we want to see all the orders that were ordered after certain date and shipped to 2 cities in France. Okay. Now we have three databases, very different databases, two document databases, one relational, and RabbitDB and MongoDB are pretty different, both in syntax and how they work behind the scenes. They are not, even the languages they are written on are different. But are those queries different? I'd say under the hood, not really. Let's assume we have a document that looks like this, the order document. And we have in a ship to embedded object, we have city and country. That's the fields I want to query on, right, in such a query. Okay, so we define an index. This red circle is a bit off, I think. When we define city and country, first city, then country as keys to index. That's index definition of MongoDB. And then we start doing queries. We query first city, and we get results, and we see index scan. That's nice. Then we try to find by country, and then we see collection scan. Not so nice. And why it's not so nice? Because index scan is a logarithmic operation which is scalable, and collection scan is not really scalable operation, it's a linear operation. Why does this happen? It's very simple. First, as you see here, of, as you see here, there is something called a reverse index or indexing table. The idea here is that your search term is essentially a hash map between your search term and where it relates, where it resides. So your search term and in which documents or records it is contained, right? So you can look up, just like you have a phone book that you can look up by names, something like that. The idea is that in some databases like MongoDB, the indexes are stored as a B tree. And this means if you index over multiple fields, your indexing terms, in this case, is a city and a country, just as we specified, are prefixed, not prefixed, but joined into one single search term. And such a query that I've shown, it searches by prefix. And this means that if you defined in an index city first, then country, this means that when you look for a city, it will find it very fast because, by the way, reverse index is sorted by its key. That is why if you can search, if you can do a binary search by its search term, it's the ideal. It's the ideal option. So essentially, what happens when you search by city, you search by prefix, and when you search by country, you cannot search by prefix because the city is second. If you define, for example, the index the other way around, first country then city, you will have the reverse situation. You will be able to search by country efficiently, and by city with linear complexity, which is not very good. In some other databases, for example, RavenDB or any Lucene-based index, your search terms are stored in separate reverse indexes. And this means that if you do a query on one of the fields over this index, it will find very fast because it can do a binary search both by city and by country because there's two separate indexing tables. And if you do a where clause with multiple filters like where, city, and country, then it will need to do union or intersect and other set-based operators depending on the logical operator you use. And this means that you should take into account this kind of peculiarities, and you should take into account, if you remember how indexes work at least approximately, it will be easy to see why sometimes you get collection scan, why sometimes you get index scan. And for large enough amount of data, the difference can be really huge. Now, let's dig a bit deeper into indexes. As I mentioned, indexes are trees, usually B trees, but they don't have to. They can be they can use tre, for example, TRIE. They can use all sorts of uh, data structures for that, but usually it's tree derived, some kind of tree, usually B tree, because that's the best way of one of the best, if not the best way of storing data in your hard drive. It's optimized for reads, and that's usually what you do with indexes, you read them. But updates, because the trees are usually self-optimizing, the updates of index usually have non-trivial complexity. And thus, databases that update indexes as part of their data changes, for pretty much all relational databases, for example, will have less and less throughput when you define more and more indexes, because indexes have overhead, and those databases update indexes as part of your data change. So another reason that you need to find golden path with amount of indexes versus the performance of writes. Now, if you take a look at the complexity, even simple query will have non-trivial complexity, because here we have two filtering clause and they all have logarithmic complexity, but the merge between them is linear pretty much. And if we consider relational databases, then the join algorithms have also non-trivial complexity. So this kind of thing, when you see, considering this information, when you see a query like this, yes, this is a real query. You can see in many queries of this kind, you can see many relational databases of legacy systems, and 10 join statements is quite a lot. And I've seen queries for more join statements. And if you also add a where clause, this means you have a problem. Most likely you have a problem on your hands with large enough databases. And we don't want our queries to be of too much complexity. And we can do quite a lot to at least mitigate the effect of the complexity of queries and indexes. First, proper indexes, as I mentioned, too much indexes will cost you in performance. Too little indexes will cost you in performance. Of now it's query performance. So there needs to be a golden path between them, and optimizations are pretty important. Quite often you can remove at least some of the joins and maybe rearrange your data to need less joins. And if in extreme cases you might also join tables and do all sorts of denormalization just for specific types of data or specific tables. Just if you have, let's say, hundreds of billions of rows, you might need that kind of optimization. Of course, things like any operations that are not set-based in relational databases are a big no-no, because they have horrible performance. And subqueries, I've seen horrible queries, horrible performing queries with lots of subqueries. This is something that's very expensive to do a subquery. And also order by, some people I've seen are surprised by performance cost of order by. It's pretty expensive. So if you can avoid it, just don't use order by, especially if the query, if you have to query over a large amount of data. If you have small tables, then I guess you won't care. And then you have other types of optimizations which are more vendor specific. For example, if you have hierarchical queries, you have hierarchical keys. For in MS SQL, you have hierarchical keys that can gain performance boost if you have certain type of queries. NoSQL, it's a bit different story, because NoSQL is very different, and in order to be used in a performant manner, NoSQL requires, any NoSQL by the way, not just RavenDB, it requires different mindset. In general, data modeling in NoSQL databases has enough material by itself to last for a full day workshop. But in short, I like to say that relational databases is all about the questions you want to, it's about the answers you want to have, In NoSQL, it's about the questions you want to ask. So you need to custom tailor your data to the queries you want to do. You need to denormalize, you need to utilize domain-driven design, because document databases and graph databases map very well, their data maps very well to domain-driven design. So it's a long story, but if you model your data for NoSQL databases in the same way you model for relational database, you will have performance problems, and I've seen it happen quite often. And another thing to consider, the how you plan your queries and indexing. Just to give you a small example, here is a MapReduce query for MongoDB. Let's assume you have a database that stores authors and their blogs, and we want to count how many blogs per author we have. Okay. Now, it's a pretty simple JavaScript code to create a MapReduce, but usually in production you will have, due to various business rules and business logic, you'll most likely have much more complex code than this for MapReduce. So remember, this is actually a code that runs within database. It has complexity. So if you have an opportunity to create, let's say, linear complexity code instead of square complexity, O n squared complexity code, use it. Don't leave it like that and hope the database handles it. It will handle it, but it will cost you with performance. The same kind of logic, for example, can be applied to RavenDB. You see here a definition of RavenDB MapReduce index. And in RavenDB, as I mentioned before, the indexes are defined by C# link, which is used as DSL. Here you define group by company with all sorts of aggregations. Let's say in that online web store, something like that. And C# link, because it's compiled under the hood with Roslyn to actual C# code, C# link has a overhead and complexity by itself and some hidden allocations. And also, if you do, for example, string manipulation, string concatenation, stuff like that in a RavenDB index, it will cost you also in memory allocations, which in turn makes garbage collector do more work, which in turn makes the whole database process slower because of garbage collector pauses. So when you have any kind of DSL, when you have any kind of index definitions that you can play around with, remember that any bells and whistles have performance costs involved, and indexing more often than not, also even in databases where you don't have a DSL, such as let's say MS SQL, you still have all sorts of bells and whistles to try and optimize indexes, to try and lessen the work you do. So if you can, optimize what you can, because databases more often than not are the bottleneck of any application, and less about the performance of application itself. So why not get rid of the application of the bottleneck? Sorry. To sum it up, databases are not magic, they're abstractions, and they're leaky abstractions. And I've seen it happens when doing support for RavenDB. I've seen it happens many times. I've seen it happen many times that developers think of NoSQL, for example, as just a quirky, weird SQL database and treat it with this logic, and it is not so. Databases are applications with their quirks and gotchas and abstractions, And the performance issues, if you know a little bit about databases and how they work under the hood, you can predict, mitigate, and sometimes prevent performance issues. So that's about it. And now time for questions. You can see here links if you're curious. The mail, I forgot to change it. It's gmail.com. It's not Hibernate Rhinos. I don't work for Hibernate Rhinos anymore. And you can see GitHub repository for RavenDB. It's an open source database. You can take a look at its code. Very interesting read. And also you can take a look at the code for the experiment I did with LMDB and transaction latencies, and see for maybe even try for yourself. Thank you, and this is time for questions, I guess.
Yeah, thank you very much, Michael. And we have one question about other tools or frameworks that you could recommend for easily writing load tests for measuring database performance.
This depends. This depends on the database itself, of its protocol, of what protocol it has, with what kind of clients and which languages protocols it has. If the database has REST API, you can start from simply issuing REST-based calls, because there's plenty of tools of doing load tests for HTTP. Then there is load test frameworks. I've seen one in Python, for example, one of the more famous, forgot its name, one in C#, that you can just write code and the library will take this code and execute in parallel manner. Essentially, there are frameworks for that. Just a second, I think I can tell you its name. No, I don't remember by heart, but in general, any load test frameworks that can execute our code in distributed manner can generate enough load for a database to test that.
You can share then a link on the chat when you find.
Yeah,
it will be available. So we're already running out of time. Sorry?
In Q&A or chat?
In the chat. Q&A, only me and you can see.
Okay.
Thank you, Michael, for so detailed explanation of database internals. Fortunately, we are running out of time, and we will start next presentation without a break. So I just want to remind that you can reach Michael in the speakers room, and if you have other questions related to the database, so you can ask him in the speakers room directly. So our next speaker will be Luke Dice, and Luke will share lessons he learned about designing and running mission-critical services on the cloud. So, and we will start the presentation in 2 minutes. So, very short break. So one more time, thank you, Michael. Thank you for joining us today.
And I'm not sure, I don't remember exactly where do I end session now, right?
Yeah, I will stop the session.
Okay.
Yeah, thank you.